is machine learning, a perceptron. Now this is our bias term as 1, which we always put in. Our weights are from 0 to some m, and our matrices up to some x of m. Now we feed it through a net input function and an activation function. We get our output and we can propagate the error backwards. But this is a basic perceptron algorithm. It was an early precursor to the neural networks and so on. Now it has a binary classification, 1 positive and -1 negative. But then we define an activation function phi of z that takes a linear combination of a certain input value x and corresponding weight vector w, where z is the net input, z equals all of these here, w1, x1 and so on. So w equals this and now x equals this. Now if the activation of a sample x of I, say, that is as an output, that is the output of phi of z, is greater than some threshold theta, we predict 1 and class -1 otherwise. In the perceptron, the activation function phi is a simple unit step function, which is sometimes called the Heaviside step function, given here. We can bring theta to the left hand side and define a weight function as this, where x of 0 equals 1, so that we can write z in a more compact form, which should be more familiar here, which this is the Heaviside component. So when the superscript t is the transpose, which transforms a column vector into a row vector and vice versa, our z, it becomes this here. And is a quick example, multiplying these, and hence this is the transpose of this. You should know anyway, it's linear algebra. Now 1, initialize weights to be 0 or small random numbers. 2, for each training sample x of I, perform the steps. 1, compute input y hat. 2, update the weights. Here the output value is the class label predicted by the unit step function, and the update of each weight wj is the weight vector, and it can be written as this. The value of delta wj is often is used to update the weight wj, and is calculated by perceptron learning rule given here, where our new I think that's what it's called, is the learning rate, a constant between 0 and 1. Now y of I is the true class label of the ith training sample, and y at of I is the predicted class label. And we know all weights in a weight vector are updated simultaneously, which means we don't compute the y hat I before all the weights delta wj were updated. Now for a 2D data set, we would write the updates as such, delta w0, delta w1, and so on and so on. Example, we'll take our delta wj as this new -1 which equals 0, which gives us this. However, in this case, of a wrong prediction, the weights are pushed towards the direction of the positive or negative target classes, thus here. Now, to get a better idea for the multiplicative factor x to the j, xj to the I, let's go through another example where y to the I equals plus I, and y hat to the I equals -1, and nu equals 1. And let's assume that x to j of I equals 0.5. And we misclassify the sample as -1 in this case. We would increase the weight to 1. So the activation x of j to the I multiplied by wj to the I will be more positive the next time, so we will be more likely above the threshold of the unit step function to classify the sample as +1. Now our delta wj to the I, if we're plugging in this 1 minus 1, and this is the learning rate multiplied by 0.5, we'll get this here, 1. The weight update is proportional to the value x to the j to the I. For example, if we have a smaller sample, x to the j to the I equals 2, that is wrongly classified as -1, we would push the decision boundary to an even larger extent to classify this sample correctly the next time. Hence, there's an example here. Now, convergence of a perceptron is the only guaranteed if two classes are linear separable and the learning rate is small. Now, it's just a quick introduction to some of the machine learning things where it all began as the perceptron classification. Please do like and subscribe, there's lots more to come.